Oh, cool. Cool.
Yeah, so good to be talking to you again, Dave. Yeah, like I said, we've been out of town for almost 6 weeks. Just a crazy September and first week of October, just insane. So I haven't had time to breathe, basically. But I mean, it's all been good. It's all good. But then when you come back from all that craziness and then all of a sudden you're just confronted by normal life again, it's all very confusing.
You see that the rest of the world has also been moving along, and you're like, oh God, okay, let me catch up for a second. Yeah.
Yeah, for sure. Well, so I told you I had some questions about astrophysics, and when I had the question, I thought, I know who could answer that. Dave could answer that for me. So I've been rereading this book by Matthieu Pageau,
Okay.
The Language of Creation. Have you heard of it? Very interesting book. It's an analysis of the symbolism in the book of Genesis.
Cool. What's it called?
The Language of Creation.
Cool. I'll check that out.
I mean, as a computer guy, I think you'd like it because it's got all these diagrams in it.
Oh, that's great. And the thing you said that I really liked, I think I mentioned that I was going to start.
Yes, it got all these like diagrams. See?
That's awesome. I mentioned to you that I was going to start going through the Old Testament and the New Testament, and so I got myself a copy. It's actually right here. But I've been, one of the things that I'm noticing while I'm making notes here is that I'm really zeroing in on the language that they're using and stuff. And I would show you, it's all that's what you wouldn't be able to see my notes. Well, yeah, you can kind of see that. But so that sounds really interesting. I definitely have been trying to zero in on the choice of words and stuff. Now this I realize is an abridged version, but I mean, I don't think I was going to read the Greek Old Testament.
You have an abridged version?
I assume it is because there's lots of parts of this. Yeah, like this is like definitely for.
Oh, the story of the Bible. Okay, so that's not the Bible itself.
Yeah. Okay, that explains it. But I was interested in this. I mean, I think I know the story by now. But I still like the choice of words used to describe God. But this does explain a lot because I was like, that's why I said it's like an abridged version. But now I see it's just the story of the Bible.
So who's the author?
This is by Tan Books. Doesn't actually say an author here.
Oh, yeah, so it's just kind of a generic thing that's been compiled by.
Right. And there's like a part 2 New Testament one as well. The Old Testament, and there's the New Testament. I think there's a third book too. Yeah.
Well, that's interesting. Yeah, I will say one thing though, just so once you feel like familiar with that, you probably would be a good idea to go back and actually read the actual like book of Genesis, because in one place, I think it might be in the book of, it's in one of the prophets, God says that there is power in my words. My words do not go out and come back void. My words have power in them. So when we read about the Bible, we're not getting the same power that we're getting when we read the Bible.
No, absolutely. And like this is purchasing this book. I have this bad habit of like, I'm like, I need this thing. And then I go shopping for it. And I don't really look at what I'm buying. I'm just like, well, enough people purchased this. So I think this is exactly what I need. And so that's what happened here. We're like,
that's why my Kindle is all jammed up. I'm just jammed. I've got thousands of books in Kindle, and now I don't even look at it because it's like overwhelming.
Well, because it's only now that I'm suddenly remembering that the entire reason that I had put it off was because like I didn't know how to get my hands on Genesis or like what order to read things in and stuff. And now like I started reading this and I was so fascinated by the like story that I completely forgot that I originally wanted to read the actual text. So you bring up a great point. I'm looking.
Well, it's not a bad idea to have. It's not a bad idea to have the big picture in mind before you start reading.
Yeah, because I really am like, I think the first time that I learned any of this stuff was like literally April.
Mm-hmm.
Or then all I knew about was there was a guy on a cross. Like,
Uh-huh.
yeah. But now I'm getting an idea of the story and stuff. But I think I told you before that like it was really the story that really made me deeply involved in it. Like in a weird way, I think it connects to me on an actor level, like having these characters to learn from, these parables and stuff like that. And I've just been going down this huge rabbit hole of oral history and tradition and stuff like that. All this crazy.
There's a wonderful book. Do I have it here? It must be in another room, but it's called What the Bible is All About.
What is that book about?
What the Bible is All About. And the author's name is Henrietta Mears, Mears.
Interesting.
Now, Henrietta Mears was a great Bible teacher that taught Sunday school for young men for many, many decades. And this book came out of her teaching of all these young men and all their questions and everything.
Oh,
and
cool.
She wrote this book, What the Bible is All About. It's probably, I want to say 100 years old, but it's timeless. And what she does is she looks at every book in the Bible and shows you where Jesus shows up in that book, because Jesus shows up even in all the Old Testament books. We don't realize that because when you're reading it, yeah. So she goes through the whole Bible and shows you where his story is embedded in every book in the Bible.
Yeah. Well, and even when you said her creation of that book is actually spot on to what I was saying before too, where one of the things I've been teaching my students, I mean, I want to hammer this a little bit more, is that like when you are given a character to portray, and if this character is a decently made character, you're kind of portraying, this is like Peterson talks about these meta characters and stuff like that. Like there's like a father, but then there's a meta father. And I try to teach my students that like as an actor, you are portraying the meta character. You're not portraying just a guy, you're not just portraying your dad. You're portraying the meta father that needs to be in this scene, this type of character that has been abstracted out of many different things from the director's point of view and the writer's point of view. But in the exact same way, it's like, I like the idea that this came from listening to students and organically being like, and that's also part of the oral tradition too, is like, I was reading about the Iliad and Odyssey and stuff like that, and how most likely those ancient battles, what was happening was some big battle happened, we all know that. But what I really like is that there are these people passing on oral traditions and stuff we can learn from the big battles. And what I realized is that if you could imagine it in a moment-to-moment kind of way, a bard going around talking to people, sometimes people are like, that's not true. I don't believe in that at all. You completely forgot about Jesus or something like that. Then the bard will just quickly be like, I forgot to mention this part also. And then the oral tradition just starts to absorb other people's problems. And it's like, now do you see how it applies to your thing? And it's like, oh, okay. And so it's cool. I read how the Iliad and the Odyssey and stuff, one of the reasons that they became so epic is because it took hundreds of years and they just kept absorbing little things here and there. They're like, oh, that's true. We forgot about that guy. Yeah, he was there too. That's true. So like, I don't know. It's a cool connection between oral tradition and meta characters.
When you were talking about that, for some reason, I started thinking about all like the great generals throughout history that have studied the art of war and have looked at all the great battles and tried to distill from the great battles what can be learned and what can be seen about the way human beings operate and all of that. Yeah, that's fascinating.
Yeah.
Well, so to get back to my question at hand, because I know your time is limited. I've been reading this book, and one of the things he starts talking about is the difference between time and space. Okay, and so that really interests me because I've done a lot of work on my channel on the concept of entropy and the arrow of time. And it's such a big, vast, complex topic. But I don't want to go into all of that right now, but I did want to ask a question about the universe, because if we're thinking about space, obviously the universe is supposed to be this space-time manifold. I mean, that's what Einstein said, right? That,
Yep.
yeah, that it's all one thing, that space and time actually aren't separate.
Right.
But Matthieu in the book is talking about the way that space and time are referenced in the scripture, and that space has this meaning of has a symbolic meaning of something stable and ordered, and time has this symbolic meaning of change. And change, and you could say maybe completeness. In other words, all the potential resides in time, but that which has already been ordered resides in space. So it's almost, the picture he's drawing is pretty similar to Jordan Peterson's picture of the known and the unknown. Space being the known and time being the unknown.
Absolutely.
I mean, it's not a perfect mapping, but but it got me thinking about the pictures that I've seen, and I'll pull this up on the screen here. If I can remember how to do this, share screen. Honestly, I'm so out of practice. It's just crazy. Must be on this page. Let's see if we got this. The shape of the universe, cosmic inflation. You can see this? You've seen these illustrations, right?
Oh, yeah.
What happened at the Big Bang, the cosmic inflation is the first little part when it expands out, like here, expands out. And then my picture is, and I think this is correct, that the universe is flat. It's a disk. Now, whether these labels are correct or not, I don't know. But I mean, it doesn't really matter. They're all the same. I'm just trying to pull up a bigger picture of it so you can see better.
So I will say one unfortunate consequence of these types of images is that they do give the impression that the universe expands as a disk. But really, for what we see, the universe we're talking about expands more like a cube, like any sort of volume expands. It's a volume and it is expanding. It's not flat like this. It would be as if the room we're in just started moving apart in every direction, just widening.
Well, right. So, well, one of the things that I was reading about what shape is the universe, is talking about there's a debate going on right now whether the universe is flat or a sphere. Apparently, some researchers saw something in the cosmic microwave background radiation that indicated that potentially the universe is a sphere, but then everybody else said, no, really, that's just an anomaly in those measurements. Really, it's flat as far as the eye can see. Which is a condition there as far as the eye can see. But anyway, let's just assume that the universe is like a disk or is flat like paper, and that it can extend out infinitely in all directions, right? Then these pictures, what I want to get at is these pictures like this. This is the disk, and this is the disk later in time, and this is the disk later in time yet, and this is the disk at our current time.
Yes.
And that this big shape here, this big bell shape, is really just the working. This is just the passage of time. This is the movement of the disk through the passage of time. Would that be correct?
On that axis, yeah.
Yeah. So the disk is just moving out. So at any moment in time, it's just a slice of this.
Correct.
This slice back here is a slice that was there 8 billion years ago or something.
Correct. Yep.
Okay.
And actually, it's funny, the stuff you're talking about right now, my boss, when I was an astrophysicist, was a cosmologist, and I was a cosmologist in training. So this is all cosmos stuff. So we're talking very specifically about my research, like Like we're hitting exactly the stuff that I know. And I can tell you one interesting thing that this diagram does not really talk about, but it might be like too much. It's an important thing that I think is useful, but like if you could consider the edge of this object that you're seeing, how it's like, you know, it looks like it's containing everything. Technically, and I wish scientists did a little bit of a better job making this note, that boundary is what we call the observable universe. And by all means, we do assume there is a universe beyond that boundary. It's just that we haven't ever seen it. And as scientists, we can't make any assumptions about it.
Well, so that was one of my other questions, is that this makes it look as if there's something outside of this.
And we assume there is, but we never talk about it as scientists. Anytime you hear the universe, we're only talking about that colored bubble. And it's what we really should say is the observable universe.
Okay, so there is the observable universe, and we don't know at what point the universe might end. It could just keep going and going and going and going, in which case there would be nothing outside. There would only be the universe.
Right. And now you're talking about the unobservable universe, where, like, I think this is a perfectly valid conversation, but I will say you won't ever hear a scientific conversation about an unobservable thing.
Right. Yeah. I got, because that's the unknown, right? But I mean, that's where scientists get their questions, is in the unknown.
This is why I like to bring it up, is because like scientists and science enthusiasts, proper scientists understand the limits of science. They call it the observable limits of science. But science enthusiasts are like, no, science is foolproof and there's no place for blah, 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 or blah, 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 or blah, blah, blah. And it's like, I don't think you understand how limited science is. Like, that's a big area that's unobservable. You know, it's so I don't know. I like to point that out. And again, like my boss and stuff, they're good scientists who point that out. You know, we're only talking within the limits of what we understand. And I like to point out that we've only been doing this research for the last like 30 to 50 years. So like the fact that we're like, the universe is accelerating, it's like, maybe we should just wait 30 years and check it again.
Yeah. So one of the things that I heard, I like to listen to Sabina Hassenfelder. You've heard her before? Oh, she's a wonderful, she's a physicist. I don't think her specialty is astrophysics, but she talks about everything. She has a YouTube channel and she just talks about things. One of the things she mentioned the other day, and she might have been, sometimes she mentions things ironically. So I'm not sure if she was saying it actually exists or not, but she mentioned the universal attractor.
Oh, yeah.
Like,
I mean,
somebody had asked her, why, so, you know, everything is moving. We're not only moving through time, everything is also moving through space. Correct?
Yeah.
That the universe is expanding, which means all the galaxies are getting further apart from each other.
Right.
But the whole thing is also moving. But
not as largely as you would think. It mostly moves in small pockets that sometimes get very large. So there's one thing, you could image search this really quickly. Well, let me see if this would bring up an image. It's the Laniakea Cluster. Yeah, the Laniakea supercluster. Yeah, and if you look at an image of that, you'll see what I'm talking about. This is one of the largest objects of just things that are all attached to each other and seem to be affecting one another. But once you get beyond this, there are scales where we don't really seem to see things affecting one another too much. But I still think that they do, or there's some sort of underlying thing we don't know yet.
Well, so when they say that when they show those pictures of our solar system moving through space, with the sun moving through space, with all the planets trailing behind and going round and round, and then that's also part of our galaxy, which is going round and round and moving through space.
And then our galaxy is part of another local cluster.
Right.
But then after that, it ends for us. Well, not really. We're also part of a supercluster. I think we're actually part of this Laniakea supercluster.
So in other words, the whole universe itself may or may not be moving as a unit.
Yes, yes. I would agree with that.
Okay. Well, so then the universal attractor is something that is attracting all of the superclusters.
So that's where I'm a little confused. So there is a thing, I think it's called the Great, is it called the Great
Attractor?
Yeah, I think it's called the Great Attractor. And I don't know if it's called the Universal Attractor, but there's a Great Attractor, which is what's pulling the Laniakea Cluster. And
Well,
we don't know
that's what she said. She said the Great Attractor. I made a mistake when I said that.
Yeah, and it's pulling the Laniakea Cluster, and we don't know what it is. I'm kind of a fan of, like, you know, if a river all flows into one area, it doesn't mean necessarily that something pulled the river into that area. Like, it may have just found its way there and collected there. So I'm kind of a fan of that idea, but I know exactly what you're talking about, Great Attractor, and I don't know much about the Great Attractor. But yeah, there's a Wikipedia article on it.
Well, so I guess my question was, if everything in the universe is moving apart, is it moving apart because it's being drawn apart, or because it's being repelled apart?
Good question. So this is one of the biggest mysteries in physics. As a famous little line, this is actually one of the things Einstein went to his deathbed super embarrassed about. He thought he just had it totally wrong, and he was really ashamed about his conclusion on it. But then his conclusion on it, even though it's a big question mark, is still the closest we've ever come to things expanding. But here's the idea. So first off, that's what dark energy is. And I don't like that term because of this. Like, dark energy, there's gravity that pulls things together. Dark energy almost gives the impression that something's pushing or like pulling things apart. But if you study cosmology enough, I think what's really happening is more like what I said with the room idea, where what I like to imagine is that in between space between us, like if you could imagine the negative zone, just nothing's there. For some reason or another, it's duplicating, and making everything between it further apart. And so it's happening in a three-dimensional way. So this cube that I'm in is just getting bigger and bigger and bigger and bigger and bigger. And so that's the repelling force. It's not really a force. It's just, for some reason, things are expanding and gravity can't keep up with it. So it appears to be a force. And we don't know why.
And the dark energy is just a way of accounting for that expansion.
That's exactly the right word to use, because what dark energy comes up only in energy equations when you're talking about radiation energy and mass energy and this energy and dark energy. So that's when dark energy comes up. Einstein called it his cosmological constant, which was just the cosmos seems to be growing at a constant rate, and so he called it the cosmological constant. Yeah, so we don't have an explanation for that. A lot of people have put forth tons of theories, and I only remember one of them because I was a big fan of one of them, and then I was fortunate enough to be in grad school when it was debunked. Like, rarely do theories get thoroughly debunked, but this one just got flat out debunked. Like, they found a measurement that was like, this is impossible. So I was like, oh wow, the one that I was rooting for is impossible. So
do you remember what it was?
Yeah, I think it was called the brain world model, which it's brain BRANE. And the idea is that, like, our universe at the Big Bang, there may have been another universe that was created alongside it. And as they, like, it's weird, as they separate on another type of dimension, they're kind of losing their ability to hold themselves together. And so they're splitting up easier as they separate from one another. And then the further they get, they're just going to start off another one. But somebody debunked that. I get blown away. Like, I remember watching that lecture, and then my boss told me this measurement's going to come out soon and it'll either make it or break it. I was like, how could you possibly measure this weird thing? But like, I guess they debugged it. Yeah.
Well, they find something else to measure that has
That's
something
exactly
to do
it.
with that, right?
Yeah, they try to find 2 or 3 peripheral things that all overlap. And they're like, okay, well, I was looking at the sun, you were looking at Mercury, and we both saw the exact same thing. Like,
Yeah, I mean, it's like those guys that came up with the measurement where they said maybe the universe is a sphere instead of a flat disk, was a measurement that they were doing of some Planck distance in the cosmic microwave background radiation. And you wouldn't think that would have anything to do with it being a disk. But if that measurement is of a certain nature, then gravity pulls the whole thing up together into a disk.
Well, and one thing that's funny is that, like, I don't remember the specifics, but I remember there's an entire chapter. I have the book on the other side of this wall. There's an entire chapter in one of my cosmology books that's specifically about how the CMB, the cosmic microwave background, can be used to determine the flatness of the universe, and how, like, since it's so far back, we can take a measurement now, we can use that as an old measurement and then kind of compare the two, as long as we know the time frames. Something like that.
So when they take these measurements, are they, now this is probably a really stupid question, but we're here.
Yeah.
And so they're looking out at the entire observable universe, up, over, under, around. I mean, as if I were the center of a sphere, I'm looking out and measuring.
Yeah, in fact, what you can see, if you go to images real quick, this is super quick. If you do the CMB dipole.
Well, maybe I can just let you share a screen.
Yeah, that's a good idea. Yeah, then I can walk through this real quick. Because this is a funny little thing. There's a drunk history on this, and I made the mistake of correcting them in the YouTube comments. Then I had a whole swarm of people trying to correct me.
It doesn't help to correct anybody in the YouTube comments.
Yeah, no, that was a mistake. This is the CMB dipole. So this is the CMB that Planck made just a few years ago. Mm-hmm. And it's a high resolution image of the universe, like you said. The cool thing about the dipole is, I can't see. Okay. Basically, if you can imagine Earth and like just one telescope pointing out of Earth, and it's spinning like this, and it's going through the galaxy and all these things and spinning around and stuff. It's spinning and catching light, and then like the Doppler effect. That's effectively what you're seeing here as it spins through the Milky Way. So our telescope, the first measurements that it took of this, like it looking all over the universe, it got one half of the universe really red and one half of the universe really blue. And then we started subtracting all these like peculiar movements. So the first big one is our, I wonder, I'm not sure what that is. But basically the idea is, I think so. The idea is we first had this middle one. I don't know what this is. First we had this, and then we subtracted the rotation of the Milky Way. And then we got this, and this red thing here is probably the Milky Way obscuring our view. Like the camera works great everywhere but the Milky Way. You know what I mean? Because it's like right in front of us.
So if the universe were a disk and we're looking out and we're just seeing the edge of the disk, that's the cosmic microwave background radiation that we're seeing.
But the cosmic microwave background, like this is very much like a globe.
Yeah, that's obviously. But so then, if the universe is a disk, how can the cosmic microwave background radiation be a globe?
Right. So
how can we be in the center of it?
Yeah. So here's the thing that I would add to the disk idea. It's fine to think of these as disks. Everything you said in the conversation is totally accurate. The one thing I would add is that each slice in that thing is, rather than a 2-dimensional slice, it's actually an entire 3-dimensional slice. You have to blow it up.
Mm-hmm.
And then it makes sense. So like each slice has its own three-dimensional universe.
But when you say that it has a three-dimensional universe, is that only a mathematical three-dimensionality?
It's the full three dimensions. So like, for instance,
So it is a sphere.
It is a sphere. Yeah. Yeah. Or a cube. I like to think of it as cube, but yeah. Yeah. Sphere. I guess sphere makes more sense. That's the observable universe would be a sphere. Yeah.
Well, or I guess it could be a cylinder.
I don't think we see any evidence of that. And it would have to be like a cylinder on the unobservable universe, because the observable universe has followed all the ideas that we keep putting out so far. One weird thing about astrophysics that people don't talk about, it makes sense not to talk about, but like the distances in astrophysics are so long that like once we start talking about cosmological stuff, planetary people don't really have a say in it. And the rungs to get up to that level, sometimes they're so dependent on one another. We really try to make them known. But there is a problem in astronomy where like it's called the astronomy ladder or something like that, where if one of the rungs
measurement ladder, the way you measure one thing and then use that as a kind of a jumping off point.
Right. And so if one of those breaks, a bunch of them breaks. And we've gotten better at that. But astronomy is definitely one of the fields that has ladders.
Mm-hmm.
Yeah.
Yeah, I watched something where they talked about the Cepheid.
The Cepheid variables.
And that's one of the things that they use to tell you, because that's
actually a great example.
Standard light, a standard amount of light that's given off by that. So it's a very good measurement tool.
Yeah, that's what Hubble did. And he's the first one, because this is the mind-blowing thing that he reveals to people, and that other scientists were like, you're crazy, this is ridiculous. Before Hubble's point, everybody thought that we would see a bunch of stars, and then sometimes we'd see Andromeda, which is another galaxy. And they would see Andromeda. They would see the spirals and everything. But they thought Andromeda was a weird thing in our galaxy. They thought it was like some small like star or something like that looked weird. Not a star, but they didn't know what it was. And he was the first one that was like, it's nowhere near us. It's really far away, and it's so bright that we could see it. And they were like, that's insane. Like, how far away are you talking about? And like, he basically was saying, like, it's not in our neighbor's backyard. It's in a different country's backyard. Like, it's very far away from us. So it's actually quite cool how but that's a great example of a rung, where it's just like, if you're willing to believe that because he looked at a few stars, you know, it's suddenly millions of miles away. Okay, I guess. But then we backed it up with other things too. It is crazy, some of these things that we're like, I don't know, like how different all of a sudden we shifted things. I feel bad for some physicists back then, and I'm sure some people nowadays do. I mean, I'm not a physicist anymore.
Yeah, I mean, things have changed a lot during my lifetime. This whole idea of there being so many different galaxies, and you know, when you see those pictures of the universe and they zoom in on one quadrant, and then you zoom in within that quadrant on one galaxy, and then on, you know what I mean? It's just
like, I often
get down to this tiny little thing, and it's actually an entire galaxy, you know?
Yeah, I often forget that all these images and stuff were really only like made since the 80s and stuff. 80s and 90s. 90s is when really, I remember reading it. There's a bunch of astro stuff that we figured out then, but
yeah.
Yeah.
Well, so, okay, so I'm almost finished. I think, I think that was.
Yeah, take your time if you have enough.
Yeah, when we look out. Oh, the other thing is darkness. I remember reading an article recently on why is there so much darkness in the universe when we look out in the night sky. I mean, if there's all these galaxies and stars, and yet, and all those stars are letting off lots and lots and lots of light, and yet there's all this darkness out there in the in-between. And the article I read was very unsatisfying. So you have something better here, huh?
Yeah, so what you're talking about is Olbers paradox, which is if there's so many stars out there, why isn't our sky filled with light? Or why is it so dark instead of just super bright. And in fact, that was what Einstein, so physicists have this funny little thing where once they've made it, they're just like, well, let me take a crack at this thing. Let me try this thing. And so Einstein gave a shot at Olbers paradox. And Einstein's solution, after writing all the imaginative stuff he came down with, was that's where he created the cosmological constant. And I like this story because it's effectively, imagine the smartest guy you know. Every time he runs the calculation, he's always 5 off. And so finally, to make it correct, he just says +5. And they're like, where did this 5 come from? He's like, I don't know, man. It's, you have to say +5. That's how Einstein felt, where he was like, I keep being off, but it is the same amount that I'm off by. So I'm just going to call it a constant. And like, he felt so silly, but that was his answer to Olbers paradox. And back then, they didn't have stuff to back it up. He just threw in a number and was just like, this is Einstein cosmological constant. I wonder if it's even here.
Well, that's really funny because my mother was a bank teller in her youth. And she said the hardest thing about being a bank teller is that at the end of every day, you have to balance your cash box. You know, people are coming in, they're putting a certain amount of money in their accounts, and then you give them cash back. You know, they give you a check or they give you some large bills and you give them back small bills, or, you know, very many ways that this money is being transacted. At the end of the day, you have to be exact, not within 5 cents. You have to be exact.
Mm-hmm.
And so even if you're off by 2 pennies, they can't just say, oh, well, it's just 2 cents. Just
Right.
go on to tomorrow, because it could be an error of 1 million versus $999,998 on the other side. And so, or actually 98 cents on the other side. So it could be 2 massive errors with this difference of 2 pennies. And so you can't just let the 2 pennies go. But yet we do this.
No, it is really funny. But like, one thing that's funny is that going back to his goofiness is that like, he was so bummed out that his answer was just like, +5. That's the only way it works. I'm not sure. Sorry, guys. And then he died like that. He died thinking he never figured it out. But yeah, the only thing that explains this adequately is invoking space-time expansion, and that is his constant. Like, before anybody else observed the expansion of space, Einstein was there saying like, it must be expanding. Like, I can't think of any other way for us to not see a bright sky other than it has to be expanding too far. Like, he said, things are moving away from us, and that's why we don't see it. And people were like, that's kind of odd. Are you sure? And he said, I don't like it. I hate this idea, but that's the only thing I've got. And then he died like that. And like, I think we just had his 100-year death anniversary a few years ago. And so like, it's cool that we kind of were able to, well, it's cool that since then, nobody else has really figured out a better way of explaining it.
So in other words, at some time in the past, there was not as much darkness.
In other words, it's actually written right here. I just saw it. Basically, what happens is that the farthest things, the stars that we would hope to see, are so far away that they are getting redshifted as they get to us, and so their light is getting to us, but much longer than those of visible light, and so it appears dark to the naked eye. And as a show of that, we could actually go to the cosmic microwave background, where it's not in the visible light, but it does pop up in the microwave. And so we call this a picture of the Big Bang because we're looking that far back.
Mm-hmm. Yeah.
Yeah.
This is like, I don't know what, one second or one something after the Big Bang.
Something, very, very small amount of time. And this is effectively that Olbers paradox answer. This is the night sky lit up.
And as I understand it, the difference in temperature between the blue and the orange is almost infinitesimal.
Right. Very, very, very.
Okay, well, you've given me something to chew on. I can go back to reading my book and see if I can figure things out.
Sure. Let me know if you have any other questions. I hope I didn't, like, I always go too far into random bits of astro stuff, but
Oh, no, I like random. I like
Okay.
random. So, how would you feel about publishing this? Or are you still on the not published side of
Yeah,
things?
no. I think this is just fine. Yeah.
Okay.
Yeah, the
Because
last
I think
one.
it might be fun for people to hear me ask dumb questions. and you
Sure,
answer.
sure. And me give my, like, every time I give science answers, I always get a horde of people who are like, this guy doesn't know what he's talking about. And like, I don't know. I like it because, like, scientists, I'm happy to disagree with scientists. Science enthusiasts, I think it's kind of funny when they disagree with me because it's like, back up any of what you're saying and then let's go. But like scientists, again, like, they often bring me down and stuff, and I can, we go back and forth. But all the questions you asked today was pretty easy, I think. So, yeah.
Well, I mean, an actual scientist is going to be talking about measurements and
And they're actually
observations, and science enthusiasts are all, the science is finished, it's done.
right, exactly. Like the scientists, they'll get on me for not being specific enough.
Mhm.
Science enthusiasts will get on me. They'll get on me for all sorts of things. If I get the vibe that they get on me if I don't say science the way that they want it to be said. But I don't know. Science is a very careful thing. Everybody who does it is very careful about it. We know our limits.
Mhm.
Yeah.
Well, it's great talking to you, Dave. Thank you
All right,
for
great
being
talking to you.
available.
All right, cool.
Okay. Bye-bye.
All right, I'll see you.